Two major earthquakes hit Indonesia in 13 hours, at opposite ends of an archipelago 2,800 kilometres wide. The first, a magnitude 7.7 off the coast of Flores, put 26,000 people inside a zone of violent shaking and sent a tsunami warning across 4 provinces before sunrise. The second, a magnitude 6.9 beneath Sumatra, was felt in a different country and broke almost nothing. Every instinct you have says those two events must be connected. The physics says they are not, and the reason why opens onto something much larger, because 11 major earthquakes have struck this planet in 226 days, and sitting in that same catalogue is a number nobody has been reading. It is not 11. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment and tell me where you're watching from tonight. Let's get into it. Part 1. 13 hours, 2,800 kilometres. At 5:58 in the morning, on the north coast of Flores, the ground stopped behaving like ground. It was still dark. The fishing boats were already out. In the villages strung along the coast road between Enda and Mbay, people were awake in the way people are awake before dawn in a tropical fishing town, which is to say half of them were making coffee, and the other half were still deciding whether to get up. And then the floor moved, and it kept moving, and it did not stop for somewhere in the region of a minute and a half. The United States Geological Survey put it at magnitude 7.7. The epicenter sat 68 kilometres north-northwest of the city of Enda, out under the Flores Sea, at a depth the agency initially gave as 10 kilometres. The European Mediterranean Seismological Centre disagreed slightly and said 35. Either way, this was a shallow earthquake, and shallow is the word that decides everything about what happens next. Within 4 minutes, Indonesia's meteorology, climatology, and geophysics agency had issued a tsunami warning covering 22 separate areas across 4 provinces. Within 15 minutes, the first aftershock above magnitude 5.9 had already arrived. Within 30 minutes, there had been 3 of them, the largest at magnitude 6.1. And then, 13 hours later, it happened again. Not there, 2,800 kilometres away. At 54 minutes past 10 in the morning, Coordinated Universal Time, which is 54 minutes past 5 in the evening in western Indonesia, a magnitude 6.9 earthquake struck beneath the island of Sumatra. The epicenter was placed near the city of Pematang Siantar in North Sumatra province, about 126 kilometres southeast of Medan. Indonesia's own agency put it slightly differently, at magnitude 6.4, centred 10 kilometres southeast of Simalungun. People felt it in Medan. People felt it across the Strait of Malacca, in Malaysia, in a different country entirely. 2 major earthquakes, 1 nation, 13 hours apart. Before we go any further into the why, let me give you the scale of the first one, because the numbers are worth hearing in sequence. The Geological Survey's shaking model, which estimates how hard the ground moved and how many people were standing on it, put 26,000 people inside the zone of violent shaking. That is the second highest category on the intensity scale that gets used for this, the level at which well-built ordinary structures suffer serious damage and poorly built ones are destroyed outright. Another 558,000 people sat inside the severe band immediately outside it. Widen the circle and the numbers climb the way they always do. 420,000 at very strong, 1.17 million at strong, 2.7 million at moderate, and over 11 million people who felt something. 11 million people felt this earthquake. That is roughly the population of Greece, all of them registering at some level a fault moving under the Flores Sea. The nearest cities to the epicenter give you the geography. Ende, with about 87,000 people, 68 kilometres to the south-southeast. Malmö, another 87,000, 100 kilometres to the east-southeast. Ruteng, 41,000, 105 kilometres to the west-southwest. Labuan Bajo, the tourist gateway to Komodo, 188,000 people, 165 kilometres west. And Kupang, the provincial capital, 442,000 people, 325 kilometres to the southeast. The aftershocks began almost immediately. Magnitude 5.9 at 15 minutes past 10, Coordinated Universal Time. Magnitude 5.63 minutes later. Magnitude 6.1 at 28 minutes past. Within a few hours, the count of aftershocks above magnitude 4.5 had passed a dozen. If you have never lived through an aftershock sequence, understand what that means on the ground. For people who had just run out of collapsing houses into the dark, the ground did not settle. It kept reminding them. I want you to notice what your brain just did, because mine did the same thing. 2 big earthquakes, same country, same day, and something in the back of your skull says, those are connected. That is not a stupid instinct. It is a pattern recognition system that kept your ancestors alive, and it fires hard when 2 large things happen close together in time. So let me give you the answer early, because you deserve it early, and because the honest answer is more interesting than the dramatic one. Those 2 earthquakes almost certainly had nothing to do with each other. Not, we do not know yet. Not, scientists are investigating a possible link. The physics is fairly clear on this one, and I will walk you through exactly why, in detail, later on. But here is the short version. The Flores earthquake happened 10 kilometres below the seafloor, on a fault that pushes the wrong way relative to everything around it. The Sumatra earthquake happened 172 kilometres down, inside a slab of ocean floor that is being swallowed into the mantle, under pressures where rock is not supposed to be able to snap at all. They are not the same kind of earthquake. They are not on the same structure. They are separated by a distance roughly equivalent to London to Moscow, and the way stress travels through the crust does not work over that distance in any way that could make one cause the other. They are 2 entirely separate expressions of the same enormous, slow planetary machine. The Australian plate is driving north into Southeast Asia at about 70 millimetres a year, which is roughly the speed your fingernails grow. That single, boring, unstoppable motion is what built Indonesia, what feeds its 130 volcanoes, and what broke 2 completely different faults in one day. Think about what 70 millimetres a year actually does over geological time. It is 7 metres a century, 7 kilometres in 1,000,000 years. The Australian continent has been travelling north for tens of millions of years, and everything in its path has either been crumpled up, shoved underneath, or melted. Indonesia is the wreckage of that collision, and the reason it has more active volcanoes than any other country on Earth is that it sits directly on top of the seam. So when 2 earthquakes happen in Indonesia on the same day, they are not connected in the way people mean when they say connected. They are connected the way 2 potholes on the same road are connected. Same road, same traffic, same weather, no causal link between them whatsoever. So if the 2 Indonesian earthquakes are not connected, that ought to close the question. Except it does not, and here is why. Because 5 days before Flores, a magnitude 7.4 earthquake had struck Western Colombia and killed a number of people that has been climbing ever since. Because a few hours before the Sumatra event, a magnitude 5.2 woke up an entire Spanish province in the middle of the night and forced a regional government to activate an emergency plan. Because when you put all of that on one map, on 1 week, it does not look like coincidence. It looks like the planet leaning into something, and that is the question this is really about. Not whether Flores caused Sumatra. That one has an answer. The real question is bigger and messier. Are monster earthquakes actually ramping up across the globe right now, or does it only feel that way? I went and counted. Not estimated, not vibed, counted, using the same open catalogue anyone with an internet connection can download. In the 226 days of 2026 that had elapsed by the 14th of August, exactly 11 earthquakes of magnitude 7.0 or greater had struck the planet. Hold that number. 11. I will tell you in a moment what the long-term average is, and whether 11 is high, and the answer might annoy you, because it annoyed me. But there is a second number in that same catalogue, and it is the one almost nobody is looking at, and it is the reason I ended up making this video instead of a straightforward breaking news report about an earthquake in Indonesia. That number is 0. I will come back to it. First, we need to understand what actually broke off the coast of Flores, because the fault that produced this earthquake is one of the strangest structures in the entire Ring of Fire. It points the wrong direction, and the map that governments and insurers and ordinary people use to understand its danger has a flaw in it that puts the hazard significantly closer to shore than anyone reading that map would assume. Part 2. The fault that thrusts backwards. Almost everything you have ever heard about subduction zones describes a machine that runs one way. An oceanic plate, cold and dense and heavy with water, arrives at the edge of a continent or an island arc, and it goes down. It bends into a trench, it slides beneath the lighter plate above it, and as it descends it drags on the underside of that plate, loading it like a bow being pulled. Every few centuries the bow releases, the upper plate springs seaward and upward, the seafloor jumps, and a tsunami crosses an ocean. That is Sumatra in 2004. That is Japan in 2011. That is Cascadia, waiting. South of the island chain that contains Flores, that exact machine is running right now. The Australian plate is subducting northward beneath the Sunda plate, and the proof is stacked above it in the form of one of the most beautiful and most dangerous volcanic arcs on Earth, the chain that runs from Java through Bali, Lombok, Sumbawa and Flores, and on east toward Timor. But the earthquake on the 14th of August did not happen there. It happened on the other side of the islands, on the north coast, and it happened on a fault that dips the opposite way. The structure is called the Flores thrust, and it is what geologists call a back thrust. Instead of the ocean plate diving under the arc itself is being shoved up and over the southern edge of the Sunda plate to the north. Picture two people pushing a rug from opposite ends until it buckles in the middle. The main subduction zone is one hand. The back thrust is the wrinkle that pops up behind it, running parallel, dipping the wrong way, absorbing the compression that the main fault cannot. Structures like this exist elsewhere. The Woodlark region east of Papua New Guinea has one, but they are genuinely uncommon, and the two geologists who published the fastest serious analysis of this earthquake, Kyle Bradley and Judith Hubbard, describe volcanic back thrusts as, in their words, fairly uncommon and not particularly well understood, either from geological or hazard perspectives. Sit with that phrasing for a second. Not well understood from a hazard perspective. That is a sentence about a fault that just produced a magnitude 7.7 earthquake next to a populated coastline, written by two of the people who have published the most about it. Here is how we know it was the Flores thrust and not the main subduction zone. When you cut a cross-section through the island from south to north and plot every recorded earthquake in that slice, you can literally see the descending slab. The earthquakes trace a plane sloping down into the mantle, deeper and deeper toward the north, exactly the way the physics says a subducting sheet of ocean floor should behave. The 14th of August event does not sit on that plane. It sits far above it, near the surface, in the overriding crust. It is not a subduction earthquake at all. It is the arc itself tearing. The moment tensor confirms it. Every earthquake mechanism has two possible fault planes, and you need geology to decide which one actually moved. In this case, the lower angle, south-dipping plane matches the Flores thrust, and the dip read straight off the Geological Survey's own solution is 29 degrees. Now here is where it gets genuinely important, and where the story stops being an academic point about fault geometry and becomes something with a body count attached. The Flores thrust does not have one dip. It has two. Far out in the deep water of the Flores basin, the fault is almost flat. It dips only a few degrees off horizontal, and it has grown outward through the soft sediment that blankets the seafloor, crumpling that sediment upward into folds. That flat, shallow outer portion is what almost every published map draws when it draws the Flores thrust. It is a line, out in deep water, at the northern edge of all that folding, and as far as anyone can tell, that outer portion does not produce large earthquakes at all. It may simply creep, sliding a millimetre or two a year, releasing its stress quietly and continuously without ever snapping. The part that snaps is somewhere else entirely. Closer to land, the fault steepens into a ramp, dipping at something in the region of 25 degrees, and that ramp is the seismogenic zone. That is the part that locks, loads, and fails violently. Do you see the problem? The line on the map is out in deep water. The earthquakes come from a structure much closer to shore. Anyone looking at that map to estimate how far the danger sits from their village is reading a number that is too big. This is not speculation. Kyle Bradley was a co-author on a 2021 paper in the journal Science Advances, led by Karen Lithgow, which imaged exactly this two-part geometry over on Lombok to the west, using industry seismic reflection data for the shallow flat section and earthquake focal mechanisms for the deeper ramp. The paper's title tells you how strange this fault is on its own terms. It is about thermal squeezing of the seismogenic zone on what they call the volcano-rooted Flores thrust. The heat from the volcanic arc above compresses the depth range in which the fault is capable of breaking, squeezing the earthquake-producing layer into a narrow band, and the new earthquake fits the old model immediately. When you plot the locations of the aftershocks onto the structural map produced by Eli Silver and his colleagues from a multi-beam survey of this exact seafloor back in 1986. The aftershocks fall in the shallower water close to the coast, on the ramp, not out at the front of the thrust belt in deep water. Take a moment on that 1986 survey, because there is something quietly astonishing about it. A multi-beam survey is a ship dragging an array of sonar transducers back and forth across the ocean, fanning sound down onto the seafloor and timing the echoes, building up a topographic map of terrain no human will ever see. Silver and his colleagues did that across the Flores back arc thrust belt 4 decades ago, published it in the Journal of Geophysical Research, and mapped a landscape of folds and faults in the deep basin north of the island. That survey was motivated by the geological questions of its era, not by seismic hazard. Nobody ran it to work out where an earthquake would kill people, and yet, as Bradley and Hubbard note, it remains, to their knowledge, the best available view of the seafloor and subsurface structure in this area. 1986. 4 decades of satellite technology, and the sharpest picture we have of the ground beneath a fault that just produced a magnitude 7.7 earthquake next to a populated coast is a paper old enough to have been typeset by hand. There is newer work. In 2024, Harisma Andikagumi and Kyle Bradley published a model of the entire Flores thrust in the journal Tectonics, combining seismic data with an assessment of coastal geomorphology to work out where the coastline is rising over long timescales and where it is sinking. Coastlines record fault behaviour. If the ramp beneath you is repeatedly thrusting land upward, you get raised marine terraces, old beaches stranded metres above the current sea level, coral reefs left high and dry. If the geometry puts you on the down-going side, you get drowned features instead. Their model identified raised coastal terraces along the western part of what turned out to be this earthquake's rupture area, and subsiding coastal features along the eastern part. The reason is geometric. The ramp fault likely sits farther offshore in the east than it does in the west, which means the earthquake that just happened should have physically changed the coastline of Flores in opposite directions at its 2 ends, and that when survey teams get out there with instruments, the deformation they measure will be one of the strongest constraints anyone has on where exactly the fault broke. That is the thing about a large earthquake in a poorly instrumented place. The best data does not come from the seismometers, it comes from the coral. There is one open dispute worth flagging now because it will matter later. The Geological Survey released a preliminary slip model within hours, and it broadly agrees with the geology. An east-to-west rupture, dipping south, with a maximum slip of 2.6 metres. 2.6 metres of the crust jumping over its neighbour in under a minute. But the orientation of that modelled fault, derived largely from the seismic waves themselves, sits at an angle to the north coast of Flores, rather than running parallel to it the way the geological map of the ramp does. Bradley and Hubbard flag the consequence plainly. The casualty and shaking estimates depend on that model, and, in their words, it is possible that a fault model running more east-west would have different impacts. 13 of those aftershocks, at magnitude 4.5 or greater, spread across roughly 160 kilometres of distance in the first hours. That is not scattered noise. 160 kilometres is almost exactly the rupture length you would predict for a magnitude 7.7 earthquake. The aftershocks are outlining the tear, and they tell you one more thing. The main shock epicenter sits at the eastern end of that 160-kilometre stripe, which means the rupture did not start in the middle and spread both ways. It started in the east, and it ran west. That matters for who got hit hardest. It matters for the casualty estimates that were still being revised as I put this together, and it matters for the question of where this fault might break next. But before any of that, there was a much more immediate question hanging over 22 coastal districts in 4 provinces in the dark that morning, and it was the oldest question in the Indonesian archipelago. How big is the wave? Part 3. 94 centimetres. The warning went out fast. Indonesia's Geophysics Agency runs one of the most heavily exercised tsunami warning systems on Earth, for the simple and terrible reason that it has had the most practice. Within minutes of the rupture, modelling had been run and alerts had been issued for 22 areas across 4 provinces, and the instruction attached to them was not advisory language. Local governments were told to direct residents to evacuate and to keep them away from beaches and riverbanks. Read the list of places and you get a sense of the geographic reach. In East Nusa Tenggara, North Manggarai, Northern Garda, the northern part of West Manggarai, North Enda, Enda Island, North Sika, Sika Island, northeastern Flores. In West Nusa Tenggara, Sangiang Island, Gili Island, North Bima City, North Dompu. Across the water in South Sulawesi, Silaya, Jeneponto, Bantaeng, Takalar, Bone, Wajo, East Luwu, North Luwu, Palopo City, and in southeast Sulawesi, Bau City. Estimated arrival times ran from 4 minutes after the earthquake to an hour and 43 minutes after it. Some of those communities had less time than it takes to boil a kettle. That spread of arrival times tells you something about the physics of tsunami propagation that people often get wrong. A tsunami is not a wall of water racing across the ocean surface. It is a disturbance of the entire water column, from seabed to surface, and its speed is governed almost entirely by water depth. In the deep open ocean, it can travel at the speed of a commercial jet. In shallow coastal water, it slows dramatically, and as it slows, the energy that was spread through kilometres of depth gets compressed into meters, and the wave grows. Which is why the communities 4 minutes away and the communities an hour and 43 minutes away were being warned by the same bulletin. The Flores Sea is a complicated basin with shallow shelves and deep troughs, and the wave from a rupture in the middle of it does not spread out in neat circles. It refracts, it bends around islands, it speeds up over deep water and slows over shallow, and the arrival time at any given beach depends on the entire bathymetric path between there and the fault. A tsunami did arrive. That is worth saying plainly, because the story that ended up circulating afterward was that the warning had been cancelled, and a lot of people read cancelled as meaning nothing happened. Something happened. Wave heights of roughly 20 to 50 centimetres were recorded at multiple locations, and the largest observed wave came ashore at Morol, in Enda Regency, about 50 kilometres east of the epicentre. It measured 94 centimetres, just over 3 feet. 3 feet of moving seawater will knock an adult off their feet. It will fill a ground floor. It will not, however, erase a village. Now hold that number, 94 centimetres, against the number this same fault produced 34 years ago. On the 12th of December, 1992, a magnitude 7.7 earthquake, some catalogues say 7.8, struck beneath the northern coastline of Flores, effectively the same size, effectively the same place, on the same fault system. It was the deadliest earthquake anywhere in the world that year. At least 2,500 people died, and researchers who went back through the toll afterward concluded that roughly half of those deaths were caused not by the shaking but by the water. The run-ups from the 1992 tsunami exceeded 20 metres in places. Some measurements put the maximum above 25. That is a wall of water taller than a 6-storey building arriving on a coastline of single-storey houses. 25 metres then, 94 centimetres now. Same fault, same magnitude, 34 years apart. What changed? The leading explanation for 1992 is that the earthquake triggered a submarine landslide. When a slope of waterlogged sediment on the seafloor lets go, it displaces an enormous volume of water very suddenly and very locally, and the resulting wave can dwarf anything the fault motion alone would generate. It is also brutally focused. A landslide tsunami can be catastrophic along 30 kilometres of coast and barely register 200 kilometres away. So the honest reading of the 14th of August is not that Flores got lucky in some vague cosmic sense. It is that, as far as anyone can currently tell, a slope did not fail. The difference between 1 metre and 25 metres on this particular stretch of seafloor may come down to whether a pile of mud decided to stay where it was. That is not a comforting mechanism. It is a coin flip built into the geology, and it sits underneath one of the most tsunami-exposed coastlines on the planet. There is a third data point on this same fault system, and it argues the same way. In 2018, the Flores thrust broke again, further west, beneath the island of Lombok. It broke twice, in a dual rupture that produced 2 separate magnitude 6.9 earthquakes. The shaking devastated Lombok. Villages in the north of the island were flattened, hundreds of people died, and the tourist economy of a place that had been marketed for years as the quieter alternative to Bali collapsed overnight. And those 2 earthquakes raised no significant tsunami at all. Same fault system. 2 magnitude 6.9s, no wave. Go back further and the pattern gets older than instruments. In 1820, a large earthquake struck the Lesser Sunda Islands and Sulawesi to the north, producing shaking across an enormous area and a locally damaging tsunami. The most likely source, based on where the reports came from, was the Flores thrust, somewhere west of where it broke this month. 2 centuries ago, on the same structure, with no seismometers and no warning system, and no way to record anything except what people wrote down afterward. So the ledger of this one fault reads, a damaging tsunami in 1820, a catastrophic 25-metre landslide enhanced tsunami in 1992, no meaningful tsunami from 2 magnitude 6.9s in 2018, and a 94-centimetre wave in 2026. The published assessments give the flora's back arc thrust a maximum credible magnitude somewhere around 7.8 to 7.9, which means the earthquake that just happened came close to the ceiling of what this fault is thought to be able to produce. It came close to the ceiling, and it produced a wave you could stand up in. That is the range. That is what the same structure is capable of, depending on variables nobody can see in advance. There is one more thread in the tsunami story worth pulling, because it is a genuine piece of public safety information, and it gets taught wrong constantly. Reports from the coast that morning describe people who felt the shaking and immediately headed for high ground, and specifically people who did so after watching the ocean pull back from the shore. That instinct saved lives. It has saved a great many lives since 2004, when the Indian Ocean tsunami killed around 227,000 people and permanently rewired public awareness across the region. But the receding ocean is not a reliable signal, and Bradley and Hubbard were careful to say so. A tsunami is a wave, and a wave has a polarity. Depending on which way the seafloor moved and which part of the wave reaches you first, the sea may withdraw before it arrives, or it may simply arrive. Plenty of tsunamis have come ashore with no warning drawback at all, and the reverse trap exists too. Fault slip can permanently lift or drop the ground surface along a coastline, and if the land under a bay rises by a metre, the sea will appear to retreat, and it will stay retreated, and no wave is coming. The rule that actually works is the boring one. If you feel strong shaking near a coast, do not wait for the water to tell you anything. Go up. Whether anyone had time to go up in the villages closest to the rupture is a question that was still being answered as I recorded this, because the roads into the worst affected regency were blocked by landslides and the phones were down. Part 4. The earthquake that happened inside the plate. 13 hours after the flora's rupture, the second earthquake struck, and almost nothing about it resembled the first. Start with where. Pematang Siantar is an inland city in North Sumatra province, home to a few 100,000 people, sitting in the highlands southeast of Medan, on the road that tourists take toward Lake Toba. The epicenter was placed within a handful of kilometres of it. Indonesia's agency put the centre 10 to 11 kilometres southeast of Simalungun. This was not an offshore earthquake. There was no coast between the fault and the people. Now, the depth. The Geological Survey's solution gave 172 kilometres, and some reporting derived from the same catalogue said 183. Indonesia's agency gave 163. Whichever figure eventually survives review, we are talking about an earthquake that happened somewhere between 160 and 180 kilometres below the surface. Let me put that in a frame that means something. Commercial aircraft cruise at about 11 kilometres. The deepest hole humans have ever drilled, the Kola Super Deep borehole in northwest Russia, reached just over 12 kilometres after 2 decades of effort and had to be abandoned because the rock at the bottom behaved like plastic. This earthquake happened roughly 14 times deeper than the deepest hole we have ever managed to dig, and that is where it stops being a normal earthquake and starts being a genuine physics problem. At 170 kilometres depth, the weight of everything above you produces pressures in the range of several gigapascals. Under that kind of confining pressure, rock is not supposed to fracture. It should deform, flow, creep, behave like something between a solid and an extraordinarily stiff fluid. Brittle failure, the sudden snap that generates an earthquake, requires the two sides of a fault to overcome friction and slide, and friction scales with the pressure squeezing the fault shut. Squeeze hard enough, and the fault simply cannot slip. Push the arithmetic out to 170 kilometres, and it says earthquakes at that depth should be impossible. They are not impossible. There are thousands of them. The planet produces somewhere between 5 and 8 earthquakes of magnitude 6 or greater at depths beyond 200 kilometres in an average year, and the deepest well-recorded events reach past 600 kilometres. So how? This is not a new problem. It is one of the oldest unresolved arguments in the entire science. In the 1920s and 30s, the Japanese seismologist Kyu Wadati and the American seismologist Hugo Benioff independently noticed that if you plot earthquake locations around the Pacific margin in cross-section, They do not scatter randomly through the mantle. They organise onto inclined planes, sloping down and away from the trenches, traceable to depths of several hundred kilometres. Those planes are now called Wadati-Benioff zones, and they were the first hard evidence that something solid was descending into the mantle, decades before plate tectonics existed as a theory. Benioff published his mapping of these zones in 1949, and almost immediately the discovery created a problem, because the deepest earthquakes on those plains were happening at depths where the confining pressure should have welded any fault shut. The honest answer is that after nearly a century of work, seismology has 3 serious candidate mechanisms and has not settled on one. The first is transformational faulting. Deep inside a cold subducting slab, the mineral olivine is carried into pressure conditions where it should have converted into a denser crystal structure. But because the slab is cold, the conversion is kinetically delayed. The mineral sits there in a metastable state, out of equilibrium, like superheated water that has not yet boiled. When it finally does transform, the collapse into a denser phase can happen in a thin shear band and can run away catastrophically. That idea was developed in the late 1980s by Harry Green and Pamela Burnley. The second is dehydration embrittlement. Ocean floor arrives at a trench soaked in water, chemically bound into hydrous minerals like serpentine. As the slab descends and heats, those minerals break down and release that water as a free fluid. Fluid at depth props the fault open against the confining pressure, cutting the effective friction, and the fault becomes able to slip after all. The third is thermal shear runaway. Once a small patch of slab begins to shear, friction generates heat. Heat weakens the rock, weaker rock shears faster, and faster shearing generates more heat. A positive feedback loop that ends in a rupture. None of the 3 has won. It is entirely possible that different deep earthquakes use different mechanisms. Each of the 3 has a weakness, which is why the argument survives. Transformational faulting requires metastable olivine to still be present, and the coldest interior of a slab is the only place it can survive to great depth, which constrains where those earthquakes can happen, and struggles to explain events in warmer slabs. Dehydration embrittlement needs water, and by the time a slab reaches 400 kilometres, most of the water bound into its minerals should already have been driven off in shallower reactions, which makes it hard to explain the very deepest events. Thermal runaway works in the equations but needs something to start the shearing in the first place, which means it may be an amplifier rather than a trigger. What all 3 share is a picture of the descending slab as something under enormous internal strain. It is being pulled downward by its own excess density, bent, twisted, heated from the outside while its core stays cold, and forced through mineral phase changes on a schedule the surrounding mantle has already completed. It is not a passive sheet sinking. It is a body under stress from every direction at once, and 172 kilometres beneath North Sumatra, part of it failed. What this earthquake was, structurally, is what seismologists call an intraslab event. Not on the boundary between the 2 plates, but inside the descending Australian slab itself, 170 kilometres down and well past the point where it is still in contact with anything above it. The plate is being pulled apart and twisted by its own weight as it sinks, and something in it tore. Early independent analysis characterised the motion as a oblique slip, and the depth explained everything about the human outcome. Nobody issued a tsunami warning, and this is worth being precise about, because the language used in the coverage was that no tsunami threat resulted. That undersells it. This earthquake was not capable of producing a tsunami. To make a wave, you have to move the seafloor. A rupture 170 kilometres below an inland city displaces essentially nothing at the surface of the ocean. The tsunami risk was not low. It was structurally absent. Meanwhile, the shaking spread out in a way a shallow earthquake never does. Energy from a rupture radiates outward in expanding spheres. From 10 kilometres down, that sphere hits the surface almost immediately, in a tight and violent footprint. From 170 kilometres down, the same energy is spread across an enormous area by the time it arrives, and the high-frequency content, the sharp snap that shatters unreinforced brick, has been absorbed by all that intervening rock. What is left is long, slow, rolling motion, spread wide and thin, which is why people felt this earthquake in Medan, 126 kilometres away, and in Malaysia, across an international strait, and why initial reports describe limited damage in a city sitting almost directly above the epicentre. There is one loose thread. The Geological Survey called it magnitude 6.9. Indonesia's own agency called it magnitude 6.4. Those are not the same earthquake in energy terms. Half a magnitude unit is a factor of about 5.6 in released energy. And Indonesia's agency attached its standard disclaimer to the bulletin, which reads, in translation, that the information prioritizes speed, that the data processing results are not yet stable, and that they may change as data is completed. That disclaimer is an honest institution telling you the truth about how fast science works, and it will get quoted by people who want to argue that agencies cannot be trusted. Hold on to it. We will come back to what it actually means. The short version, for now, is that the first magnitude you see for any earthquake is produced by an automated system, reading the first few seconds of the arriving waves at whatever stations happen to report fastest. It is designed for speed, because a tsunami warning that arrives after the wave is worthless. Reviewed magnitudes come later, when a human analyst has the full waveform from a global network and can model the whole rupture rather than its opening moments. Automated solutions get revised in both directions, routinely, on almost every significant earthquake, and the revision is the system working, not the system lying. We watched this exact process play out on this channel on the 5th of August, when the Philippine agency's automatic solution for a Mindanao earthquake came in at magnitude 7.0, and the reviewed solution brought it down to 6.4, an 11-fold drop in released energy. Nobody hid anything. The first number was fast and the second number was right, because the two Indonesian earthquakes are only 2 entries in a much longer list, and it is the list, not either earthquake, that the title of this video is really about. So let me show you the ledger for 2026, all of it, and then let me show you the number in that ledger that nobody has been reading. Part 5, 11, in 226 days. Here is the full accounting. Every earthquake of magnitude 7.0 or greater recorded anywhere on Earth in 2026, up to and including Flores, in the order they happened. On the 22nd of February, magnitude 7.1, 57 kilometres north-northwest of Kota Belud in Sabah, Malaysia. And the number attached to it is one of the strangest in the whole list, a depth of 629 kilometres. That is a deep focus earthquake in the truest sense, close to the bottom of the range where earthquakes exist at all. The mechanism involved strike-slip, oblique strike-slip and reverse faulting, and it was the first magnitude 7 or greater event within 250 kilometres of that spot since 1950. Alert level, green. Essentially nothing happened at the surface, from an earthquake that would have levelled a city had it been shallow. On the 24th of March, magnitude 7.5, 158 kilometres west of Neafu, Tonga. Depth 234 kilometres. Normal faulting inside the Pacific Plate as it subducts westward beneath the Australia Plate. On the 30th of March, magnitude 7.3, 51 kilometres east-northeast of Luganville, Vanuatu, at about 121 kilometres depth. Oblique thrust faulting on one of the busiest plate boundaries anywhere. 19 earthquakes of magnitude 7 or greater have occurred within 150 kilometres of that point in the preceding century. On the 1st of April, magnitude 7.4, 129 kilometres east-southeast of Bitung, Indonesia, at roughly 35 kilometres. Reverse faulting near the interface between the subducted Halmahera slab and the overlying Sunda Plate in the tectonic knot of the Molucca Sea. Indonesia's first entry in this list, 4.5 months before its second and third. On the 20th of April, magnitude 7.4, 102 kilometres east-northeast of Miyako, Japan, at about 25 kilometres. Thrust faulting near the Japan Trench interface, and here is a detail that should raise the hair on your arm slightly. It occurred about 192 kilometres north of the rupture area of the 2011 Tohoku earthquake. The same subduction interface. The northern neighbour of the fault patch that killed nearly 20,000 people. On the 7th of June, magnitude 7.8, 25 kilometres southwest of Cablalan in the southern Philippines, at 57 kilometres depth. Thrust faulting. This one remains the largest earthquake of the year. Roughly 15 million people were exposed to moderate to severe shaking, and the alert level went orange, meaning significant damage was considered likely. On the 24th of June, magnitude 7.2, 21 kilometres east-northeast of San Felipe in northern Venezuela, at about 28 kilometres depth, and then, 39 seconds later, on the same day, in the same place, magnitude 7.5 at about 10 kilometres. Read that again. 39 seconds. The Geological Survey classified the 7.2 as a foreshock to the 7.5, which is the correct technical description, and also a wildly inadequate one, because in human terms what happened is that a country was hit by 2 magnitude 7 earthquakes inside the time it takes to read this paragraph. The second one was shallow strike slip near the boundary between the Caribbean and South American plates, and the warning issued at the time said widespread damage and high casualties were probable. On the 17th of July, magnitude 7.3, 52 kilometres west of Puerto Madero, offshore southern Mexico, at about 22 kilometres. Reverse thrust faulting in the subduction zone where the Cocos Plate descends beneath Mexico and Central America. Around 4 million people experienced moderate to very strong shaking. On the 10th of August, magnitude 7.4, near San Jose del Palmar in the department of Choco, western Colombia, at roughly 107 kilometres depth. Colombia's own geological service called it the largest magnitude earthquake recorded in the country in the 21st century. We covered it here on the 10th of August, and the story of what happened in Colombia in the days after is one I have to come back to, because it changes how you should read every casualty number in this video. And on the 14th of August, magnitude 7.7, off Flores, 11 major earthquakes in 226 days, 10 countries, 2 continents plus a scattering of island arcs, deep focus events at 600 kilometres and shallow ruptures at 10, 1 doublet separated by 39 seconds. Look at that list again and notice how much of it never reached you. Unless you follow this closely, you probably did not hear about the magnitude 7.5 off Tonga in March, because it happened at 234 kilometres depth in a part of the Pacific where the nearest substantial population is a long way from the epicentre. You probably did not hear about Vanuatu at the end of the same month, at 121 kilometres. You almost certainly did not hear about Malaysia in February, because a magnitude 7.1 at 629 kilometres depth does essentially nothing at the surface and generates no footage. And a magnitude 7 with no footage is not a news story in 2026. It is a line in a database, which means that the 11 events on this list did not arrive in your awareness as 11. They arrived as maybe 4 or 5, clustered in the ones that produced video. The Philippines in June, Venezuela's doublet in June, Mexico in July, Colombia last week, Flores this weekend. 4 of those 5 are in the last 10 weeks. That is the shape of the feeling. Not 11 earthquakes evenly spread across 8 months, but a handful of highly visible catastrophes stacked into a short window, which is a completely different psychological experience even though it is the same underlying data. I will come back to that, because it is a big part of the answer. So now the question that the whole internet has been asking in one form or another for the last week, is 11 a lot? The long-term average, established from more than a century of instrumental records, is about 16 earthquakes of magnitude 7 or greater per year worldwide. Roughly 15 of those fall in the magnitude 7 range, and about 1 is magnitude 8 or above. 16 a year, and we are at 11. Now do the arithmetic properly, because this is where almost everyone goes wrong in both directions. The 14th of August is day 226 of a 365-day year. That is 61.9% of the year gone. If earthquakes arrived at a perfectly even rate, 61.9% of 16 would be 9.9 events by that date. Expected, 9.9. Observed, 11. We are 1.1 earthquakes above the pro rata pace. That is the whole surge. 1.1 earthquakes. Now, before anyone points it out, that pro rata calculation makes an assumption, and the assumption is wrong in an interesting way. Earthquakes do not arrive at a perfectly even rate. Nothing does. If you took the number of buses arriving at a stop over a year and divided by 365, you would get a number that no individual day matches. Some days you get 3 in a row, and then nothing for an hour. The mathematical tool for exactly this situation is called a Poisson process, and it describes any sequence of independent events occurring at some average rate, where the timing of one has no bearing on the timing of the next. Radioactive decay, raindrops hitting a specific paving stone, calls arriving at a switchboard, and according to a great deal of the seismological literature, large earthquakes on a global scale, once you strip out the aftershocks that are obviously caused by their own main shocks. The key property of a Poisson process, the one that matters here, is that it is clumpy. It looks nothing like a metronome. Events bunch together and leave gaps, and if you watch one for long enough, you will absolutely see runs that feel meaningful and are not. That is not a flaw in the model. That is what randomness actually looks like, and human intuition is famously bad at recognizing it. When people are asked to write down a random sequence, they produce something far too evenly spaced, because genuine randomness looks suspiciously organized to us, and that number sits inside a statistical spread that swallows it whole. For a random process of this kind, the expected variation around a count of about 10 is roughly 3. Being 1 above the line is not a signal. It is what a normal year looks like when you check it in the middle. If you annualize the pace, 11 events in 61.9% of a year projects to about 17.8 for the full 12 months, against an average of 16. Marginally busy, utterly unremarkable. The Geological Survey says this out loud, repeatedly, in plain language. A run of large earthquakes can appear alarming, but short-term clusters are not evidence that global earthquake activity is increasing, and they are not evidence that another major earthquake is imminent. So that is the answer to the question in the title, and if the video ended here it would be a fairly boring public service announcement. Everything is normal, go about your business, the pattern you think you see is your own pattern recognition misfiring on a random process. Except that when I finished counting the 11, I noticed something else in the same catalogue. Something that is not in any of the news coverage. Something that is, statistically, extremely ordinary, and in another sense the single most interesting fact about this entire year. Part 6. The number nobody is reading. Go back to that long-term average and split it the way the Geological Survey splits it. About 16 earthquakes of magnitude 7 or greater per year, roughly 15 of them in the magnitude 7 range, and about 1 of magnitude 8 or greater, 1 magnitude 8 per year, on average, every year, somewhere. In 2026, through the 14th of August, the number of magnitude 8 or greater earthquakes recorded anywhere on the planet is 0, not 1. Not a borderline case that got revised down. 0. 226 days into a year in which 11 major earthquakes have made headlines, in which 2 hit Indonesia in 13 hours, in which Venezuela took 2 inside 40 seconds, in which Colombia recorded its largest event of the century, the Earth has not produced a single magnitude 8. I want to be extremely careful here, because this is exactly the point in a video like this where the honest thing and the dramatic thing pull apart, and where a lot of channels would take the dramatic one and run. So let me do the arithmetic before I do the atmosphere. If magnitude 8 events arrive at an average rate of 1 per year, and we are 61.9% of the way through the year, then the expected number by the 14th of August is 0.62. Not 1, 0.62. We were never owed a magnitude 8 by mid-August, and for a random arrival process with an expected count of 0.62, the probability of observing exactly 0 is the exponential of negative 0.62, which works out to about 0.54. 54%. Getting to the middle of August with no magnitude 8 is more likely than not. It is the single most probable outcome. Push it out to a full year. With an average of 1 per year, the probability that a given year produces no magnitude 8 at all is the exponential of negative 1, which is 0.368. Roughly 1 year in 3. So, statistically, unremarkable. A completely normal thing that happens about as often as rolling a 1 or a 2 on a 6-sided die. And the instrumental record backs that up. Years without a magnitude 8 are not exotic. They show up repeatedly through the 20th and 21st centuries, scattered between years that produce 2 or 3. The catalogue does not run on a schedule. There is a much more famous version of this same statistical trap, and it is worth remembering because it happened inside living memory. Between 2004 and 2011, the planet produced an extraordinary run of very large earthquakes. Sumatra, Andaman in 2004, magnitude 9.1 to 9.3. Nias in 2005, magnitude 8.6. Pisco, Peru, and Bengkulu, Sumatra, in 2007. Samoa in 2009. Maule, Chile, in 2010, magnitude 8.8. Tohoku, Japan, in 2011, magnitude 9.1. 6 great earthquakes in 7 years, after decades in which the planet had produced almost none of that size. It looked exactly like an acceleration. Serious seismologists published serious papers arguing that it was 1, and other serious seismologists published serious papers arguing that it was not. That argument is still going, and we will get into it properly shortly, because it is the reason the second half of this video's title exists. And yet, there is something genuinely strange about the shape of 2026, and the strangeness is not in either number alone, it is in the combination. The magnitude 7 count is running very slightly hot. The magnitude 8 count is running cold. The planet has spent this year releasing energy in a steady drumbeat of medium-large increments, and has not once released it in a single enormous one. And this is the exact point where the human brain produces its most seductive wrong answer. So let me give that answer its full weight before I take it apart, because it deserves a fair hearing, and because you have almost certainly already thought of it. The reasoning goes like this. The Earth accumulates strain at a roughly constant rate. Plates move at speeds that do not vary much over human timescales. That strain has to come out somewhere. If the magnitude 8s have not happened this year, then the energy that would have been released by them is still sitting in the crust, still loading, still waiting. Therefore the quiet is not reassuring. The quiet is a warning. We are overdue. It is a beautiful argument. It is intuitive. It is physical sounding. It invokes conservation of energy, and it is wrong. Here is why. Global strain is not one reservoir. It does not accumulate in a single planetary bank account that gets drawn down by earthquakes wherever they happen. It accumulates on thousands upon thousands of individual fault segments, each one with its own loading rate, its own frictional properties, its own fluid conditions, its own accumulated slip deficit, and its own history stretching back centuries or millennia. The Nankai Trough does not know what the Peru-Chile Trench is doing. The strain building on the Alpine Fault in New Zealand is not affected in any way by whether the Aleutians had a quiet year. There is no mechanism, none, by which a shortage of magnitude 8s in the first 8 months of 2026 makes a magnitude 8 more likely in September. What you're looking at when you look at that 0 and feel a chill is the gambler's fallacy applied to plate tectonics. It is the same instinct that tells a roulette player that black is due after 7 reds. The wheel does not remember. The planet does not remember either. And I want to draw a line very precisely here, because there is a version of this reasoning that is legitimate, and confusing the two is how a lot of bad earthquake content gets made. Segment-level reasoning is real. If you take one specific fault, with a known slip rate and a known history of past ruptures, then elapsed time since the last event genuinely is meaningful information. When we say the southern section of the Kurile Arc has been loaded since the 2025 rupture stopped short of it, that is a defensible statement about a specific patch of a specific fault with a specific stress change calculated for it. When we say the Cascadia margin has gone 326 years against a mean recurrence interval, that is a real number about a real structure. Global level reasoning is not real. The world is overdue for a magnitude 8 is a sentence that sounds like the Cascadia sentence and shares none of its logic. There is no global fault. There is no planetary recurrence interval. The number of magnitude 8s in a year is the sum of thousands of independent processes, and the sum of many independent random processes is, itself, random. Here is the test I use to tell the two apart, and you can apply it to anything you read. Ask, does this claim name a specific fault? The Nankai Trough has a mean recurrence interval of roughly 100 to 150 years, and last ruptured in 1946 names a fault. You can check it, you can argue about the numbers, you can look at the paleoseismic trenching that produced them. It is a scientific claim. We are due for a big one names nothing. It cannot be checked, because there is no object it refers to. It is a mood dressed as a forecast. And there is a second, sharper reason the global version fails, which is about scale. The strain released by even the largest earthquake is trivial compared to the strain stored across the planet's plate boundaries at any moment. A magnitude 9 releases roughly 2 times 10 to the 18th joules of stored strain energy. That sounds like an unimaginable number, and locally it is. Globally, it is a rounding error against the total elastic energy loaded into tens of thousands of kilometres of active plate boundary. The Earth is not a spring that gets discharged and needs recharging. It is a system so vastly overloaded, everywhere, all the time, that the release of any single earthquake barely registers against the total, which means the absence of a magnitude 8 this year has not left the planet holding anything it was not already holding. So the 0 means nothing. Statistically, mechanically, predictively, nothing, and I still cannot stop looking at it. Because here is the thing about a statistically meaningless number. It is only meaningless until it stops being 0. Sometime between now and the end of December, on any given day, that number can become 1. The probability arithmetic says the chance of at least 1 magnitude 8 in the 139 days remaining in 2026 is about 32%, roughly 1 in 3. That figure is neither reassuring nor alarming, it is just what the mathematics says, and it is a genuinely uncomfortable place to sit, because it means the honest answer to should I be worried is there is a 1 in 3 chance the year ends with a very large earthquake somewhere, and that has been true every year of your life. But before we get to what the rest of this year might hold, I owe you a correction. Earlier in this video I told you that depth is what decides the human outcome of an earthquake. That is true. It is also the kind of true that can get you badly, dangerously overconfident, and there is an example from 5 days before Flores that proves it. Part 7. What happened in Colombia after the cameras left. On the 10th of August at 34 minutes past 7 in the morning local time, a magnitude 7.4 earthquake struck western Colombia. The epicenter sat near San José del Palmar, a town of about 4,800 people in the department of Choco, roughly 280 kilometres west of Bogotá. The Geological Survey put the depth at 107 kilometres. Colombia's own Geological Service said 96. The European Centre said 95, with a slightly smaller magnitude of 7.2. All of those numbers put the rupture in the intermediate depth band, between 70 and 300 kilometres, inside the descending Nazca Plate rather than on the boundary above it. It was a strike-slip event at depth, with no surface rupture at all, and when we covered this on the 10th of August, the first-day casualty figure was around 20. 20 dead from an earthquake that released roughly 63 times the energy of the 1999 Armenia earthquake, which had killed 1,185 people in broadly the same region of the same country. The Armenia event was magnitude 6.2 at 17 kilometres depth. Shallow. It destroyed something like 60% of the building stock of a city of 300,000 people and drove a rewrite of Colombia's seismic code. 63 times the energy, 1/60th of the deaths. The lesson wrote itself, and the lesson was depth. Here is what happened to that number after the first day. By the end of the 10th of August, the confirmed toll had reached 132. By the 11th, rescuers still could not reach the epicenter, and the count had passed 200. By the 12th, Colombia's National Unit for Disaster Risk Management reported 181 confirmed, which is lower than the 200 figure only, because confirmed and reported are different words doing different work. And as of the time I'm recording this, the toll stands at least 265, with some accounts putting it at 287. It is described now as the deadliest earthquake in Colombia since the 1990s. 20 became 265. The energy ratio to Armenia is still 63-1. Depth still helped. An earthquake 63 times more powerful than the one that flattened Armenia killed roughly a quarter as many people. And that is a real and important effect that comes directly from putting the rupture 107 kilometres down instead of 17. But the comfortable version of that lesson, the version I could have told you on day 1, does not survive contact with the final number. Why did it climb like that? Part of the answer is in how casualty figures are actually built, which is a thing almost nobody thinks about until they watch a number move. A death toll is not a measurement, it is a compilation. Local officials report to regional officials, who report to a national disaster agency, which publishes a confirmed figure. Every step of that chain requires a functioning road, a functioning phone network, and a person with the authority to certify a death. When any link is broken, the number does not stay accurate and small. It stays incomplete and small, which looks identical from the outside. The Geological Survey's own alert for Colombia said as much on day 1, in its own language. The alert level was orange, and the specific estimate attached to it was roughly a 1 in 3 chance of more than 1,000 fatalities. That estimate was published while the confirmed count stood at about 20. The modelling knew what the counting did not, and the geography of Choco did the rest, because Choco is one of the hardest places in the Western Hemisphere to reach. The roads are few and bad, the rainfall is the highest in the country, which means the soil is permanently saturated, which means every seismic shake in that terrain produces landslides that then block the only roads that would let anyone into count. The Geological Survey's own assessment of the event flagged liquefaction, across an extensive area with extensive population exposed, and landslides across a significant area with significant population exposed. The predominant building type in the assessment was listed as mud wall with wood. The damage that made the news came from cities because cities are where the cameras are. The passenger terminal of Maticaña International Airport in Pereira partially collapsed, with the roof detaching over an occupied zone. More than 10 airports were affected and operations were suspended at Pereira, Manizales, Quibdó, Armenia, Cartago and Buenaventura. 34.4 million people across Colombia, Ecuador, Panama and Venezuela felt the shaking, with 1.9 million of them feeling it at very strong intensity. But the deaths accumulated in the places without cameras over days as roads were cleared. Now bring that back to Flores. As I record this, the confirmed toll from the Indonesian earthquake stands at 38 dead, 2 seriously injured, 11 with minor injuries. Around 2,000 people in Nagakeo Regency have evacuated, and the reporting from that regency says 2 specific things. Landslides have blocked the roads in, and communication signals have been disrupted. The Geological Survey's casualty modelling for Flores, after it had ingested enough data to update, moved from an initial yellow alert to an estimate that hundreds of deaths are likely. Its shaking model puts 26,000 people at violent intensity and another 558,000 at severe intensity. The building stock in the region is characterised as unreinforced brick with concrete floors and precast concrete frames with wall infill. Larger structures, schools and mosques are typically among the worst hit. 38 is not the number. 38 is the number of deaths that had been confirmed by people who could physically get to the bodies. Colombia went from 20 to 265, and Colombia is a country with better roads than the interior of Flores. I am not saying this to be grim. I am saying it because the way these numbers move is itself a piece of information, and because in about 4 days, when the Flores figure has multiplied, there will be a wave of posts claiming the initial number was deliberately suppressed. It was not suppressed. It was counted, and then the counting continued. There is a version of this that is worth being angry about, though, and it is not the counting. It is the instruments. When Bradley and Hubbard sat down to analyse the Flores earthquake, they found that the Geological Survey and the European Seismological Centre had received only a handful of felt reports from within 200 kilometres of the epicentre. And they wrote something else, which I keep turning over. They do not believe either agency has access to any local seismometers in that area. Indonesia's own agency reported the earthquake, but its public bulletin carried no intensity measurements at all. So the shaking estimates that drove the casualty projections for a magnitude 7.7 next to an inhabited coastline were built from distant stations and statistical models of how the ground usually behaves, rather than from instruments sitting on the ground that actually shook. That is not a conspiracy. It is a funding decision made over decades in a country with 17,000 islands and finite money, and it produces the same practical result as the road closures in Choco, a gap between what happened and what anyone can currently see. We ran into this exact problem yesterday, in a completely different context, looking at a submarine volcano in the Northern Marianas, where the monitoring agency itself has published the admission that without local real-time data, it cannot forecast or warn of anything. Different hazard, same hole. The planet is not under-instrumented in some abstract sense. It is under-instrumented in specific, named, predictable places, and those places are almost always the ones where the buildings are weakest. Which brings us back to the thing that keeps recurring across every event in this video, the variable that turned a 63 times Armenia earthquake into a fraction of Armenia's death toll, and turned a magnitude 6.9 directly beneath a city into a story about people feeling a bit of swaying in Malaysia. Part 8. Depth is the variable that decides. Magnitude is the number everyone knows. It is the number in every headline, the number people quote to each other, the number that determines whether an earthquake becomes an international story or a local one. Magnitude also tells you almost nothing about what an earthquake will do to human beings. Watch what happens when you sort 2026's events by depth instead. At the shallow end, Flores, magnitude 7.7 at 10 kilometres. 26,000 people subjected to violent shaking, more than 500,000 to severe shaking, buildings down across an island, roofs sitting on the ground where walls used to be, a tsunami warning across 4 provinces, and a death toll that has already reached 38, and is expected to reach into the hundreds. At 107 kilometres, Colombia. Magnitude 7.4, which is a smaller earthquake in magnitude terms, but still an enormous release of energy. 34 million people felt it across 4 countries, and the motion they described was long and rolling rather than sharp. It has killed more than 260 people, almost all of them in places where the buildings were mud and wood and the hillsides came down. At 172 kilometres, North Sumatra. Magnitude 6.9, essentially on top of an inland city. Felt in Malaysia, limited damage. And at 629 kilometres, Malaysia in February. Magnitude 7.1, which is a larger earthquake than the one that hit Sumatra this week, occurring at a depth more than 3 times greater. Alert level green, effectively nothing. 4 earthquakes, 4 depths, 4 completely different outcomes, and if you had only been given the magnitudes, you would have ranked them in almost exactly the wrong order. The physics behind this is not complicated, and it is worth walking through slowly, because once you have it, you will never read an earthquake headline the same way again. An earthquake radiates energy outward from the point of rupture in expanding waves. Think of the hypocenter as a light bulb switched on inside the Earth. The intensity of light falling on any surface depends on how far that surface is from the bulb, and it falls off with the square of the distance. Now put the bulb 10 kilometres below a village. The village is close. The energy arrives concentrated into a small, ferocious patch of ground directly above. Move the bulb to 170 kilometres. The same total energy now has to illuminate a vastly larger area by the time it reaches the surface. No point on the surface gets much. But a great many points get little, which is why deep earthquakes are felt over enormous regions and destroy almost nothing. And there is a second effect layered on top of the first, which is the one that really does the killing or the sparing. Seismic energy comes in a spectrum of frequencies. The high-frequency content, the sharp, rapid jolting, is what shatters brittle masonry, because it matches the natural resonant period of small, stiff buildings. The low-frequency content, the slow swaying, is what threatens tall buildings and long bridges. High-frequency energy attenuates faster with distance than low-frequency energy. Rock absorbs it. So by the time the waves from a 170-kilometre rupture reach the surface, the sharp destructive component has largely been filtered out, and what arrives is the long, slow roll. That is exactly what people across Colombia described. That is why a magnitude 6.9 almost directly beneath Pematang Siantar produced reports of limited damage, while a magnitude 7.7 off the Flores coast flattened buildings. There is a famous and terrible demonstration of the other half of this principle, and it is worth knowing because it is the exception that proves the rule. In 1985, a magnitude 8.0 earthquake struck off the Pacific coast of Mexico, more than 350 kilometers from Mexico City. By the time the waves reached the capital, the high-frequency energy was long gone. What arrived was slow, rolling, low-frequency motion, exactly the kind that ought to be harmless. Except Mexico City is built on the sediments of a drained lake bed, and those soft sediments amplified the low-frequency waves and rang like a bell at a period of around 2 seconds. And a 2-second period happens to match the natural sway of a building of roughly 10 to 20 stories. The mid-rise buildings of Mexico City resonated with the ground beneath them, and thousands of people died in a city hundreds of kilometers from the epicenter, while low-rise buildings around them stood untouched. The lesson is not that low-frequency motion is safe. It is that depth changes which buildings are at risk, not whether risk exists. A deep earthquake trades a small zone of total destruction for a vast zone of moderate shaking, and what happens inside that vast zone depends entirely on what has been built there and what it has been built on. Depth also governs tsunami capability, and here it is not a matter of degree, it is absolute. To generate a tsunami you have to move water, and to move water you have to move the sea floor. That requires a rupture shallow enough for the slip to propagate to the surface of the crust, and physically lift or drop the seabed. A rupture at 10 kilometers beneath the seafloor can do that. A rupture at 170 kilometers cannot, no matter how large it is. There is 170 kilometers of rock between the slip and the water, and rock does not transmit a displacement like that. That is why a magnitude 7.7 produced a 94-centimetre wave and a 4-province evacuation order, while a magnitude 6.9 13 hours later produced no warning at all. The smaller earthquake was not less dangerous because it was smaller. It was less dangerous because it was deeper, and depth is not a modifier on tsunami risk. It is a gate. Mechanism matters here too, and it is the other half of the gate. Even a shallow earthquake will not necessarily raise a wave. A strike-slip earthquake, where two blocks of crust grind past each other horizontally, moves a lot of rock sideways and very little of it up or down. Sideways motion does not displace much water. That is part of why the Venezuelan doublet in June, 2 magnitude 7s including a shallow strike-slip main shock at 10 kilometres, produced no ocean-wide alarm, and why the Colombian earthquake in August, strike-slip at depth, had its tsunami risk formally ruled out within 21 minutes. Thrust faulting is what makes tsunamis. One block riding up over another, lifting the seafloor, lifting the entire water column above it, which is exactly what the Flores thrust did, on a ramp dipping 29 degrees, with 2.6 metres of slip at its maximum. So the full checklist for whether an earthquake threatens the coast is not one question but 3. Is it shallow? Is it offshore? Is it thrusting? Flores answered yes 3 times. Sumatra failed at the first question and never got to the others. Once you have those 3 questions, you can read an earthquake bulletin faster than most news anchors can, and you will be right more often. There is a 4th question that matters just as much and never appears in a bulletin, and it is the one that ultimately decides the death toll. What is standing on top? The Geological Survey publishes a building stock assessment with every significant earthquake, and for the Flores region it reads as unreinforced brick with concrete floor and precast concrete frame with wall construction. Those 2 categories describe an enormous fraction of the housing in the developing tropics, and both of them fail in characteristic and lethal ways. Unreinforced masonry has essentially no tensile strength. It resists being squeezed and has almost nothing to offer against being shaken sideways, which is why the walls go and the concrete floor above comes straight down as a single slab. That is the mechanism behind the photograph out of Flores of a house, where the metal roof was resting directly on the ground. For Colombia, the same assessment listed the predominant building type as mud wall with wood. In Granada, it is Spanish masonry and reinforced concrete built to a modern European code in a country that has had seismic design requirements for decades. Same planet, 4 earthquakes, 4 completely different building stocks. The magnitude decides how much energy arrives. The depth decides how much of it reaches the surface and in what form. The buildings decide who walks out. Everything else in this video is geology. That last part is a policy choice, made in advance, by people who will never meet the person it saves. So when someone shows you 2 earthquakes on a map and says look how big they both were, ask the second question, how deep? Because the answer to that question determined, in the space of 13 hours in one country, whether people spent the morning running uphill or spent the evening asking each other whether they had just felt something. And with that piece in place, we can finally go back to the question I deferred at the very beginning, the one that everybody asks and that almost nobody gets a straight answer to. Can one earthquake set off another one on the far side of the world? Part 9. Can one earthquake set off another? The answer is yes, and that yes comes with so many conditions attached that by the time you've heard all of them, you will understand why it does not apply here. Start with the version that everybody agrees on, because it is not controversial at all. Earthquakes absolutely trigger other earthquakes nearby. That is what an aftershock is. When a fault ruptures, it does not just release stress, it redistributes it. The rock at the ends of the rupture and on adjacent faults gets loaded. Seismologists calculate this with something called Coulomb stress transfer, which models how much closer to failure a given patch of fault has been pushed by a neighbouring earthquake. Coulomb modelling works. It has successfully explained decades of aftershock patterns, and it explains why the great Anatolian earthquakes of the 20th century marched westward along the North Anatolian Fault, each one loading the segment beyond it, over a sequence lasting more than 60 years. But Coulomb stress transfer has a range, and the range is short. The stress change from a rupture falls off extremely quickly with distance, roughly as the cube of the distance for the relevant geometry. Within 1 or 2 fault lengths it is significant. At 10 fault lengths, it is essentially nothing. The Flores rupture was about 160 kilometres long. Sumatra is 2,800 kilometres away. That is roughly 17 rupture lengths. The static stress change delivered to a fault under Sumatra by the Flores earthquake is not small. It is unmeasurable. It is smaller than the stress change caused by the tide, smaller than the change caused by a heavy rainfall season, smaller than the change caused by atmospheric pressure moving through. Let me put a number on that, because the abstraction hides how extreme the fall-off is. If a fault 10 kilometres from a rupture experiences a stress change of, say, 1 bar, then a fault 100 kilometres away, 10 times further, experiences something on the order of 1,000th of that. Go out to 1,000 kilometres, and you're into millionths. The everyday stresses acting on the crust from things nobody considers dangerous, the twice-daily solid earth tide, the weight of a monsoon season's rainfall soaking into a mountain range, the seasonal loading and unloading of snowpack, are all larger than what Flores delivered to Sumatra. And we know those everyday stresses matter at the margins. There is a real, published literature showing that seasonal hydrological loading modulates the timing of small earthquakes. Pierre Bettinelli and colleagues showed in 2008 that Himalayan seismicity varies by around 20% with the monsoon water cycle. Kosuke Heki demonstrated a snowload signal in Japanese seismicity in 2003. Christopher Johnson, Yuning Fu and Roland Bergman published work in Science in 2017 showing that Sierra Nevada seismicity tracks hydrological loading measured by satellite positioning. Hold that thought, because it becomes important later when we get to the theories circulating about what is really driving all this. The point for now is that if a monsoon season can measurably nudge earthquake timing and the Flores rupture delivered less stress to Sumatra than a monsoon season would, then the Flores rupture did not do anything to Sumatra, so static transfer is out. Which brings us to the interesting one. Dynamic triggering is real, and it was one of the genuine surprises of late 20th century seismology. When a large earthquake occurs, it sends seismic waves around the entire planet. Surface waves in particular travel enormous distances with relatively little loss, wrapping around the globe and, for the largest events, arriving back where they started. As those waves pass through distant crust, they stress and unstress every fault they cross, thousands of kilometres from the source, and sometimes faults respond. The landmark case was the 1992 Landers earthquake in California, magnitude 7.3, after which seismologists noticed sudden increases in small earthquake activity at sites up to 1,700 kilometres away, in places like Yellowstone and the Long Valley caldera. It was not subtle in the data. Seismicity rates jumped, in some cases within minutes of the surface waves arriving. Then, in 2002, the Denali earthquake in Alaska, magnitude 7.9, did it again on a bigger scale, triggering measurable seismicity in Yellowstone, in the Utah geothermal fields, and in geyser basins across the western United States. Some geysers changed their eruption intervals. The waves from an Alaskan earthquake physically rearranged the plumbing beneath a national park 3,000 kilometers away. So the effect is not fringe science. It is documented, it is published, and there is a body of work arguing for systematic triggering at teleseismic distances following large earthquakes. More recent research has begun using remote dynamic triggering as a kind of stress meter, identifying which faults in a region are close enough to failure to respond to a passing wave from the other side of the world. Now, the conditions. Almost every documented case of dynamic triggering shares 3 features. First, the triggered events are small. We are talking about swarms of magnitude 1, 2 and 3 earthquakes, occasionally reaching into the 4s. There is no well-established case of a passing surface wave setting off a major earthquake at teleseismic distance. Second, the responsive sites are overwhelmingly geothermal, volcanic, or otherwise fluid-rich. Yellowstone, Long Valley, geyser fields, places where hot water and gas are already circulating through fractured rock at high pore pressure, so a tiny nudge can tip a fault that was already balanced on the edge. Third, the response is usually near instantaneous, occurring during the actual passage of the waves, though delayed responses over days to weeks have also been documented. Line those 3 conditions up against the earthquake beneath North Sumatra. It was magnitude 6.9, not magnitude 2. It occurred at 172 kilometers depth inside a cold, dry, descending slab, which is about as far from a fluid-rich geothermal system as it is possible to get. And the mechanics of failure down there may not even involve friction on a wet fault surface in the ordinary sense. If the deep earthquake mechanism is mineral phase transformation or thermal runaway, it is not obvious that a passing surface wave has anything to grab onto at all. A deep intraslab earthquake is, quite possibly, the single least plausible candidate for dynamic triggering in the entire catalogue of earthquake types. Think about why the geothermal cases work, because the contrast is instructive. In a geyser basin, you have rock that is already fractured, saturated with water and gas, held at high pore pressure, with faults sitting in a state of near failure that they have maintained for years. A passing surface wave arrives and cyclically stresses that rock. If the wave momentarily reduces the effective normal stress across a fault, or shakes a gas bubble loose, or perturbs the pressure in a fracture network, the system tips. The wave is not supplying the energy for the earthquake. The earthquake was already loaded. The wave is supplying the trigger. That is the whole model, and it is a good one. A triggered earthquake is one that was going to happen anyway, moved slightly earlier. It borrows from the future. Now look at where the Sumatra earthquake happened. 172 kilometres down, inside a slab that has been descending for millions of years, at pressures of several gigapascals, in rock that is cold relative to the mantle around it, and where whatever free water once existed was mostly squeezed out at much shallower depths. There is no fracture network full of circulating hot fluid. There is no near-surface geyser plumbing balanced on a knife edge. There is a slab tearing itself apart under its own weight, through mineral physics we do not fully understand. Whatever is happening down there, a surface wave from 3,000 kilometres away is not going to be the thing that decides it. And there is a timing problem on top of all of that. Surface waves from Flores would have reached Sumatra in a matter of minutes. The Sumatra earthquake happened almost 13 hours later. You can invoke delayed dynamic triggering to cover that gap, and delayed triggering is a real documented phenomenon, but every hour you add makes the association weaker, because in any 13-hour window on any day somewhere on Earth, an earthquake of some size is going to happen anyway. So here is the verdict, stated as plainly as I can. The Flores earthquake did not cause the Sumatra earthquake, not through static stress, which cannot reach. Almost certainly not through dynamic stress, which reaches but does not do this. What connects them is not one event triggering the next. What connects them is that both sit on the same plate boundary system, driven by the same convergence, and that system produces earthquakes continuously, and occasionally two of them land close together in time because that is what random processes do. That is the physics answer, and it is a solid one. But there is a much harder version of the question sitting behind it, and the honest thing to tell you is that the harder version has not been settled, and that the people arguing about it are not cranks. They are among the most respected seismologists alive, and they have been publishing against each other for 20 years. Part 10. The Argument Inside Seismology. The question is simple to state and vicious to answer. Over the whole planet, over the whole instrumental record, do great earthquakes arrive randomly, or do they cluster? Not aftershocks. Everyone agrees aftershocks cluster, by definition. Strip those out. Take only the independent main shocks, magnitude 8 and above, over the last century or so. Are they scattered like raindrops, or do they come in bursts? This sounds like a question you could settle in an afternoon. It is not, and the reason is brutal. The sample size is tiny. Magnitude 8 and above happens roughly once a year. The instrumental record with reliable global magnitudes runs back a bit over a century. That gives you something on the order of 120 events to work with, total, for the entire planet, for all of recorded seismology. 120 data points is not much when you're trying to distinguish between two hypotheses that make similar predictions. If you wanted to prove that a coin was slightly biased, say 53% heads instead of 50, 120 flips would not remotely get you there. You would need tens of thousands. Seismology does not have tens of thousands of great earthquakes. It has 120 and no way to make more. That is why this argument has lasted 20 years and will last 20 more. It is not that the scientists involved are careless. It is that the Earth does not produce data fast enough to settle it. The case for randomness is anchored in a 2012 paper in the Proceedings of the National Academy of Sciences by Peter Shearer and Philip Stark. The title is about as direct as scientific titles get. Global risk of big earthquakes has not recently increased. Their finding was that the global catalogue of large earthquakes, once foreshocks and aftershocks are removed, is statistically indistinguishable from a homogeneous random process. Whatever the 2004 to 2011 run looked like, it fell within the range of variation you would expect from a system with no memory. Andrew Michael reached compatible conclusions in Geophysical Research Letters in 2011, attributing the apparent clustering to ordinary random variability rather than any physical linkage. Charles Ammon, Thorne Lay and David Simpson had argued along similar lines in 2010, examining the Great Earthquake sequence directly and concluding that it did not represent a genuine departure from randomness. And in 2015, Eric Daub, Daniel Trugman and Paul Johnson ran Monte Carlo simulations, generating thousands of synthetic catalogues from a purely random process and comparing them to the real one. Their conclusion was that randomness could not be rejected. Notice the careful phrasing there, because it matters enormously, and it almost never survives translation into a headline. Cannot be rejected is not the same as proven false. It means the data are consistent with randomness. It does not mean the data prove randomness. And on the other side, there are serious researchers who think something more is going on. Charles Bufe and David Perkins published in 2005 arguing for genuine clustering of great earthquakes, that the temporal distribution really is non-random. That position has never been abandoned. The literature contains a persistent line of work arguing that large earthquakes worldwide are non-Poisson distributed, and that this implies some large-scale correlation mechanism we do not yet understand. What could that mechanism even be? There are candidates, and none of them are mystical. Viscoelastic stress transfer is one. The rigid crust is not the only thing that responds to a great earthquake. Beneath it, the ductile lower crust and upper mantle flow slowly in response to the stress change, over years to decades, and that slow flow can redistribute stress to distances far greater than the instantaneous elastic response reaches. It is a slow-motion version of Coulomb transfer, operating on a timescale that makes cause and effect nearly impossible to demonstrate. Slab-scale stress communication is another. If a single subducting plate is behaving as a connected mechanical body, a rupture in one part of it may alter the stress state along its length in ways that are not captured by simple elastic half-space models. And the teleseismic dynamic triggering work sits in the same territory, extended. If surface waves can demonstrably trigger small events at 1700 kilometres, the question of whether they can nudge a large fault that was already within days of failure is not absurd. It is just unproven, and there is a completely separate factor that contaminates every attempt to measure a trend, which has nothing to do with the Earth and everything to do with us. The global seismic network has grown enormously over the last 50 years. In the 1960s, the worldwide standardized seismograph network was a few hundred stations, many of them recording onto paper drums that a human being had to read. Today there are thousands of digital broadband stations streaming continuously, plus ocean bottom instruments, plus satellite geodesy measuring ground deformation directly. Detection thresholds have dropped by orders of magnitude for small earthquakes. For magnitude 8s, this matters less than you would think, because a magnitude 8 has always been detectable everywhere. You cannot hide one. But magnitude and location precision have improved, historical magnitudes have been systematically revised, and different catalogues use different magnitude scales that do not convert cleanly at the top end. Comparing a magnitude 8.1 from 1938 with a magnitude 8.1 from 2026 is not comparing identical measurements. The much bigger effect is on what reaches you. In 1965, a magnitude 7 off Vanuatu was a paragraph in a newspaper 3 days later, if it appeared at all. Today, it is an automated alert on your phone within 4 minutes, a satellite map within an hour, and vertical video from someone's kitchen within 2. The rate of earthquakes has not changed. The rate at which earthquakes arrive in your awareness has changed by an enormous factor, and there is no way for your intuition to correct for that, because your intuition was not calibrated on the old rate either. There is one more problem that sits underneath the whole debate, and it is the one I find most instructive, because it is a problem you can create yourself with a spreadsheet. It is called window selection. If you choose to compare the number of great earthquakes between 1970 and 1997 with the number between 1997 and today, you will find an enormous increase, and you can publish that on the internet in about 4 minutes. But if you had started your first window in 1960 instead of 1970, you would have captured the 1960 Chile earthquake at magnitude 9.5, the largest ever recorded, plus Alaska in 1964 at 9.2, plus the Aleutians in 1965 at 8.7. Suddenly your first window is busier than your second, and the increase evaporates. The apparent surge in great earthquakes after 2004 is, to a significant degree, an artifact of comparing it against the quiet stretch from the mid-1960s to 2003. And there is a reasonable argument that the genuine anomaly in the record is not the recent activity at all. It is that mid-century quiet. We went through all of this on this channel back on the 30th of May, when a viral statistic about megaquake counts was circulating, and I sat down and rebuilt the arithmetic from the open catalogue. The conclusion then holds now. The claim was half right about the pattern and completely wrong about the amplitude, and the moment you let someone else choose your start date, you have let them choose your answer. So where does that leave us with 11 earthquakes and no magnitude 8? It leaves us exactly where the honest scientists are. The null hypothesis of randomness has not been rejected, and there is no good evidence that global seismic risk is rising. But randomness has not been proven either. The mechanisms by which a real correlation could exist are genuine physics rather than fantasy, and the argument is still live in the journals, which is a genuinely unsatisfying answer, and it happens to be the true one. The title of this video says scientists are asking questions. That is not a rhetorical flourish. They are, and they are asking each other, in print, and they have not agreed. Part 11. 1 o'clock in the morning. In Granada. There is one more earthquake in this week, and it is the one that made the whole run feel global rather than Pacific. At 4 minutes past 1 in the morning on the 15th of August, Madrid time, a magnitude 5.2 earthquake struck the metropolitan area of Granada in southern Spain. The European Seismological Centre placed the epicenter 1 kilometre southwest of the town of Otura. Spanish reporting and the National Geographic Institute mostly put it at magnitude 5.0, with the epicenter at Alhendín, about 10 kilometres south of Granada city. The depth was extremely shallow. Some sources say 2 kilometres. 2 kilometres is essentially at the surface. Thousands of people were thrown awake. Buildings and vehicles were damaged. The Andalusian regional government activated its seismic emergency plan. The emergency line took more than 80 calls from across the region, from every province except Huelva and Cádiz, and the shaking was felt across almost all of Andalusia, into parts of Castilla-La Mancha, and reportedly as far north as Madrid. No one was killed. No serious structural damage was confirmed. Officials made a specific point of announcing that the Alhambra, the medieval Islamic palace complex above the city, and one of the most visited monuments in Europe, was undamaged. That last detail is worth pausing on, because it tells you what a government actually worries about in the first hour after an earthquake in a heritage city. The Alhambra is a 14th century complex of unreinforced masonry, plaster and timber, built on a ridge, holding up decorative work that cannot be replaced by anyone alive. It has survived earthquakes before, including whatever reached it from Arenas del Rey in 1884. But an announcement that it was fine went out fast, and it went out fast because the Alhambra is not simply a monument in Granada. In August, with the city full, it is a substantial fraction of the local economy standing inside a building that predates seismic codes by 600 years. The other thing worth noticing is the depth, 2 kilometres. If the reporting is right about that figure, this earthquake ruptured almost at the surface, which is why a magnitude 5.2 behaved the way it did. Compare it to the Sumatra event. A magnitude 6.9, which is roughly 280 times more energetic, produced less alarm in a city sitting on top of it than a magnitude 5.2 did in Granada, purely because one of them was 170 kilometres down, and the other was 2. Every thread in this story keeps arriving back at that same variable, even in a country 5,000 kilometres from the Ring of Fire. More than 35 aftershocks followed, ranging from magnitude 2.2 to 3.7, concentrated in a tight cluster of municipalities south of the city: Armilla, Alhendín, Gojar, Ogijares, Otura, and La Zubia. One more, magnitude 2.3, arrived at 16 minutes past 12 the following afternoon, 12 kilometres south of Granada at 3 kilometres depth. Now, the framing that spread online alongside this was that Granada is an extremely rare location for an earthquake, and that framing is wrong, and correcting it is worth doing, because the correction is more interesting than the claim. The Granada Basin sits inside the Betic Cordillera, and the Betic Cordillera is among the most seismically active regions in Europe. This is a diffuse plate boundary. The Eurasian and Nubian plates, Europe and Africa, are converging here at up to about 5 millimetres a year in a northwest to southeast direction, and rather than doing it along one clean fault line the way the Pacific margins do, they do it across a broad, messy zone of shallow faulting that runs through Andalusia. Local measurements from a satellite positioning network in the area show additional shortening of up to 2 millimeters a year on a fold called the Sierra de Alhama antiform. 5 millimeters a year is nothing next to Indonesia's 70. But it is not zero, and it has been running for millions of years, and Granada has the historical record to prove it. On Christmas Day, 1884, an earthquake estimated at around magnitude 6.5 struck the Arenas del Rey area, southwest of the city. It affected 14,000 square kilometres. It destroyed multiple settlements outright. It killed close to 1,000 people. The most likely source is the Ventas de Zafaria normal fault, which is regarded as the main seismogenic structure in the region and is still there. So Granada is not a place where earthquakes should not happen. It is a place where a magnitude 6.5 has already happened inside recorded history and killed 1,000 people, and where almost nobody outside Andalusia knows that. The 1884 earthquake deserves more than a footnote. It struck on the evening of the 25th of December, which meant families were indoors and gathered, in stone and mud brick houses in mountain villages that had no seismic engineering of any kind because the concept did not exist. Whole towns came apart. The relief effort became a national event in Spain, and it produced one of the earliest systematic scientific investigations of an earthquake anywhere in Europe, with French and Spanish commissions sent to map the damage and the ground rupture. And then the region went quiet for 140 years, and the memory faded the way memory always fades when the interval between events is longer than a human life, which is the real hazard in slow-moving seismic zones. Not that the earthquakes are unpredictable, but that the recurrence intervals are long enough that societies forget between them and build accordingly. The Betik Cordillera produces earthquakes on a schedule measured in centuries. Indonesia produces them on a schedule measured in decades. Both schedules are real. Only one of them is short enough for a culture to stay afraid of. You can see the difference in how the two places behaved this weekend. On Flores, people felt the shaking and ran for high ground on their own initiative, because tsunami awareness in coastal Indonesia has been rebuilt deliberately and repeatedly since 2004, and because the grandparents in those villages remember 1992. In Granada, a magnitude 5.2 produced 80 phone calls and an activated emergency plan, and, according to the reporting, a great many people standing in the street at 1 a.m. not entirely sure what they were supposed to do. That is not a criticism of anybody in Andalusia. It is the predictable outcome of a hazard that arrives once every few generations in a region where nothing that serious has happened in the lifetime of anyone currently alive. The correct reaction to Saturday morning in Granada is not that the world is behaving strangely. It is that Europe has a seismic hazard it has largely stopped thinking about, and a magnitude 5 at 2 kilometres depth was enough to activate a regional emergency plan and wake a province. Which brings us to the thing all four of these events have in common, and it has nothing to do with tectonics. Part 12. What people are saying, and what the arithmetic says. Every time a week like this happens, the same explanations surface, and I want to go through them properly rather than sneering at them, because most of them are attempts to answer a real question, with the tools someone has available. The question is legitimate. Some of the answers do not survive contact with a calculator. The first is the cascade theory. The claim is that Colombia, Flores, Sumatra and Granada form a coordinated sequence, one setting off the next around the planet, and that the authorities either have not noticed or will not say. We have already dismantled the mechanism for the Indonesian pair, extended outward, and it gets worse, not better. Colombia and Flores are on opposite sides of the Pacific, separated by an entire ocean basin and roughly 18,000 kilometres. Granada sits on a completely different plate boundary system, a slow, continental collision between Europe and Africa, with no mechanical connection to Pacific subduction of any kind. There is no pathway. What there is a pattern in attention. 4 earthquakes that each generated footage inside a window short enough that they arrived in the same scroll. The second is the suppression theory. The rate is exploding and it is being hidden. This one is the easiest to test because the data are not hidden. The Geological Survey's comprehensive catalogue is public, free, downloadable, and covers the entire instrumental era. The Global Centroid Moment Tensor Catalogue, which holds the mechanism solutions, is equally open. Every number I have quoted in this video came out of publicly accessible records that you can pull yourself this evening. There is no secret second catalogue where the real earthquakes are recorded. If the rate were exploding, You would be able to see it, and so would every graduate student on Earth, and one of them would publish it, because that is how careers get made. The third is El Niño. This one comes up constantly, and this year it has extra fuel, because a strengthening El Niño is genuinely underway. Forecasters put the probability of very strong conditions in the October to December window at around 81%. So the pattern matching is understandable. Unusual ocean state, unusual earthquake week must be connected. We ran the numbers on this in detail on the 30th of May, and the arithmetic is not close. The total atmospheric energy involved in an El Niño event is on the order of 10 to the 19th joules, but it is thermal and dispersed across an ocean basin, not mechanically concentrated on a fault. A magnitude 8 releases something like 6 times 10 to the 16th joules of stored elastic strain, and it releases it into a fault plane. Comparing the two totals is like comparing the heat in a swimming pool to the energy in a rifle bullet. The pool has more, it cannot punch a hole in anything. Where climate and earthquakes genuinely do interact is in the modulation research I mentioned earlier. Water loading, snow loading, groundwater depletion and ice mass loss all change the stress on the crust by measurable amounts, and there is a real published literature showing that this shifts the timing of earthquakes that were already close to failure by days to weeks. Tom Craig, Crystal Chenard and Eric Calais showed this for the Mississippi Basin loading the New Madrid zone. Bettinelli showed it for the Himalaya, Hecke for Japan, Johnson and Bergman for the Sierra Nevada. The stress changes involved are measured in kilopascals. Tectonic stresses on a locked fault are measured in megapascals. That is a factor of 1,000. So the honest position is that climate can nudge the schedule and cannot write it. And the cleanest counterfactual available is that the very strong El Niño of 2015 and 2016 produced no comparable seismic response at all. The fourth is the weapons theory: atmospheric heating arrays, secret devices, deliberate induction. The energy gap here is roughly 15 orders of magnitude, and I want to be clear about how large that is, because people say orders of magnitude without feeling it. 15 orders of magnitude is the difference between 1 second and 30 million years. Every ionospheric heating facility on the planet, running continuously at full power for a century, would not approach the strain energy released by a single magnitude 7 earthquake. Human beings can induce earthquakes. That part is true, and it is not fringe. Fluid injection associated with wastewater disposal has demonstrably produced earthquakes up to around magnitude 5 in a few extreme cases, and reservoir impoundment behind large dams has done something similar. But every documented case involves fluid being pumped into rock at a specific location, at a depth of a few kilometres, over months or years. There is no injection well 172 kilometres beneath Sumatra. There is no drilling rig on the floor as thrust. The fifth is pole shift or magnetic reversal. The geomagnetic field is generated by convection in the liquid outer core starting nearly 3,000 kilometres down, more than 4 times deeper than the deepest earthquake ever recorded. The field's drift is measured continuously by satellite and shows secular variation, gradual wandering, not reversal. And even if it were reversing, there is no mechanical coupling pathway from the behaviour of a fluid ion dynamo to the frictional state of a fault in the crust. Magnetism does not hold rock together. There is a variant of the suppression theory that deserves separate treatment, because it will attach itself to this particular week, and it is the magnitude discrepancy. Indonesia's agency said 6.4, the Geological Survey said 6.9. Somebody's lying, goes the argument, and the lower number is the official one because the lower number is calmer. The two agencies are measuring with different networks, at different distances, using magnitude scales that are not identical, on an event whose waveforms were still arriving when the first bulletins went out. Indonesia's agency attached a written statement to its own bulletin, saying the results were not yet stable and might change. That is not the behaviour of an institution concealing something. That is an institution publishing its uncertainty in the same message as its estimate, which is more transparency than most fields manage. And the direction of the revision is not predictable. Sometimes reviewed magnitudes go down, as happened with the Philippine event on the 5th of August. Sometimes they go up. If agencies were systematically massaging numbers downward to keep people calm, the revisions would only run one way, and they do not. And the sixth, which is the one I actually respect the most, is the version that says, I do not have a theory, it just feels like a lot. That one is correct. It is a lot. 11 major earthquakes, 2 of them in one country in 13 hours, One of them Colombia's largest of the century, and a European city woken at 1 in the morning, all inside a single stretch of days. The feeling is accurate. The inference is the part that goes wrong, and the inference goes wrong because human beings are pattern detectors operating on a random process with no memory. And I want to say one more thing about that feeling, because dismissing it as a cognitive bias is technically correct and practically useless. Your pattern detection is not malfunctioning. It is doing exactly what it evolved to do on an input it was never built for. For almost all of human history, the events a person could learn about were the events within a few days' walk. If you heard about 3 disasters in a week, they were local, and they probably were connected, and treating them as connected was the correct survival response. That instinct is old, and it is good. What has changed is the size of the input. You're now receiving the disaster feed of 8 billion people and an entire planet's crust, filtered by algorithms that specifically select for the events most likely to hold your attention. Your pattern detector is being fed a sample that was deliberately assembled to look like a pattern, and it is responding the only way it knows how. The fix is not to feel less, it is to count, which is the whole reason I sat down with the catalogue instead of the headlines, which leaves one question standing, and it is the only one that will actually be answered. Part 13, what the rest of 2026 actually looks like. I am going to give you numbers rather than predictions, because predictions in this field are worthless and numbers are not. 139 days remain in 2026. At a long-term rate of about 16 major earthquakes a year, the expected count for that remaining stretch is roughly 6. 6 more earthquakes of magnitude 7 or greater somewhere on Earth before the 31st of December. That would bring the year to 17, against an average of 16, which is the most boring possible outcome and also the most likely one. I want to be precise about what that expectation is and is not. It is not a forecast of 6 specific earthquakes. It is the average outcome of an enormous number of hypothetical remainders of 2026. The actual number could be 2. It could be 11. A random process with an expected count of 6 produces anything from about 1 to about 12 without raising a statistical eyebrow. If the year ends with 3 more, people will write that seismic activity collapsed. If it ends with 10 more, people will write that the surge accelerated. Both of those articles will be describing the same underlying rate. Where will they be? Nobody knows, and anyone who tells you otherwise is guessing. But the geography is not uniform. Roughly 80% of the world's large earthquakes occur around the Pacific Rim, and within that the subduction zones of Indonesia, the Philippines, Japan, Kamchatka, the Aleutians, Central America, Chile and Tonga carry most of the load. If 6 more arrive, the overwhelming likelihood is that most of them happen in places most people cannot find on a map, at depths that spare the surface and never reach you at all. Now the number that will not be boring. The probability of at least 1 magnitude 8 or greater earthquake before the end of the year, given an expected count of about 0.38 for the remaining period, is roughly 32%, just under 1 in 3. I said earlier that this figure is neither reassuring nor alarming, and I meant it. It has been approximately true at this point in every single year of your life. In 2 out of 3 years, nothing that large happens between mid-August and New Year. In 1 out of 3 it does. There is no way to sharpen that number, no precursor to watch, no signal that tightens it into a forecast. It is a base rate, and base rates are the only honest thing anyone has. And there is one more base rate worth knowing, because it is the question every single person in Flores is asking tonight. Was that the main event, or was it a warning? Roughly 5 to 6% of earthquakes turn out in retrospect to have been foreshocks to something larger. That number is remarkably stable across catalogues and across magnitude ranges. It means that in about 19 cases out of 20, the big one you just felt was the big one. It also means there is no forward-looking test. There is nothing measurable about a foreshock that distinguishes it from a main shock while it is happening. The classification is applied afterward, by definition, once a larger event either arrives or does not. When the 2011 Tohoku earthquake was preceded by a magnitude 7.32 days earlier, nobody watching that magnitude 7.3 could have known what it was. It was reclassified by history, so when someone asks whether the Flores earthquake was a foreshock, the only honest answer is a probability, and the probability is about 5%, and it will stay about 5% until either something larger happens or enough time passes that the question stops mattering. Closer to home, there are things worth actually watching, and they are specific. The first is the Flores aftershock sequence. There is a rule of thumb in seismology called Both's law, which observes that the largest aftershock of an earthquake tends to be about 1.2 magnitude units smaller than the main shock. For a magnitude 7.7, that gives you an expected largest aftershock of around magnitude 6.5. The largest recorded in the first half hour was 6.1, which means, statistically, there is room. A magnitude 6 or 6.5 aftershock, arriving on structures already cracked and into buildings already weakened, is a genuine and immediate danger to people who are currently sleeping outdoors because they are afraid to go back inside. The Omori law tells us the aftershock rate decays roughly, with the inverse of time since the main shock, so the hazard is highest right now and falls off through the coming weeks. The second is the direction of the rupture. The aftershocks outlined roughly 160 kilometres of fault, and the epicenter sat at the eastern end, which means the tear propagated westward. Ruptures load their own endpoints. The western terminus of this rupture is where the stress has increased, and west is where the Flores thrust runs on towards Sumbawa, toward Lombok, and eventually toward Bali. That is where the 2018 dual magnitude 6.9 earthquakes happened. That is where Lithgow and colleagues imaged the ramp geometry, and that is where the same fault system runs past coastal populations far denser than the north coast of Flores. The third is the fault model itself. The preliminary solution has the rupture oriented at an angle to the coast, while the geological mapping puts the ramp running closer to east to west. The reviewed model, which should arrive within days, will settle it, and it will move the casualty estimates with it. If the fault rotates, the shaking footprint rotates, and the estimate of how many people stood inside the violent zone changes. The fourth is Colombia, which is not finished. The toll passed 265, and the count in the mountains of Choco is still being assembled. The Geological Survey's original estimate carried a 1 in 3 chance of exceeding 1,000 fatalities, and that threshold has not been reached, but the trajectory from 20 to 265 in 5 days is not the shape of a number that has settled, and the fifth is the one I keep circling back to, because it will resolve on a fixed date whether anything happens or not. 0. On the 31st of December, 2026 will either be a year that produced a magnitude 8 or a year that did not. If it produces 1, the year was ordinary, the statistics were right, and everything in this video will look like the correct and unremarkable analysis it is. If it does not, then 2026 joins the roughly 1/3 of years in which the planet's largest earthquakes simply did not come, and it will be a footnote in a catalogue that almost nobody reads. Neither outcome tells us anything about 2027. That is the part that is genuinely hard to sit with. There is a sixth thing to watch, and it is not seismological at all. It is the coral. When a thrust fault ruptures beneath a coastline, the land above it moves permanently. Not shaking, not temporary, permanent. On the upthrown side, reefs that spent their lives just below the low tide line get lifted into the air and die, leaving a bleached band of dead coral marking exactly how much the land rose. On the downthrown side, the sea moves inland and drowns whatever was there. Those signatures last for decades, and they are the most precise measurement of fault slip that exists in places without dense instrument networks. The 2024 modelling of the Flores thrust predicted uplift along the western part of this rupture area and subsidence along the eastern part, because of where the ramp sits offshore in each place. If survey teams get out along that coastline in the coming weeks and find raised reefs to the west and drowned shoreline to the east, the model was right, and the picture of this fault gets sharper for everyone who lives along it. If they find something else, the model changes. A magnitude 7.7 earthquake is an experiment that nobody consented to and nobody can repeat. The only ethical thing to do with it is learn everything it is willing to tell you. Because we want the Earth to be telling us something. We want 11 earthquakes in 226 days to mean something, and we want the missing magnitude 8 to mean something, and we want the fact that Indonesia was hit twice in 13 hours to be a message rather than an accident of timing. The instinct that produces that want is the same instinct that produced the Wadati-Benioff zones and plate tectonics and every earthquake early warning system that has ever saved a life. Pattern recognition is not a bug, it is the entire scientific project. But the planet is not communicating. It is a heat engine 4.5 billion years into a very slow, cooling process, driving cold rock down into hot rock and hot rock up into cold, and the earthquakes are what that machine sounds like from the inside. It has been making this noise for the whole history of complex life. What changed in the last century is that we started listening, and what changed in the last decade is that we started listening in real time, all of us, at once. So the ground under Flores is still settling tonight. The count in Nagakeo is still climbing. The reviewed magnitude for Sumatra has not been published yet. Andalusia is logging its 36th aftershock, and somewhere on a subduction zone nobody in this video has named, a fault that has been loading quietly since before any of us were born is a little closer to the end of its cycle than it was this morning. Which leaves one thing that is actually checkable, and it is not the one everybody is asking about. Not whether the planet is speeding up. That question has an answer, and the answer is no. The checkable question is smaller and stranger, and it sits at the bottom of the same catalogue. With 139 days left on the clock and a 1 in 3 chance riding on it, does 2026 end with a magnitude 8, or does it end with a 0?